Hello there guys, welcome back to another video. In this one we're looking at something called simple random walks. So a simple random walk is a type of stochastic process. If you don't know what a stochastic process is, that is absolutely fine because I've got a video on it, and if you want to go and have a look in the description, you will see a video made by me about stochastic processes. If you don't want to watch the video, or if you've already seen it, that's all good. So if you've not seen the video, just a quick recap on what a stochastic process actually is. A stochastic process in the discrete case, which is what we're going to be looking at in this video, can be thought of as a sequence of random variables. Okay, that's all it is. It's a sequence where each term is a random variable. And of course, we can say bits and bobs about it. And a simple random walk is a specific type of sequence. So what we're going to say is we're going to define a random variable. I'm going to call it xi, and it can take two different values. This is what a random walk is, okay? So xi can either take the value 1 with probability p, and it can take the value -1 with probability 1 minus p, which we can also call q. So this random variable kind of looks like a Bernoulli random variable, but it's not taking the values 1 and 0, it's taking the value 1 and -1. But other than that, it's the same thing as a Bernoulli random variable. Now we're going to define Sn. So we're going to define Sn. This is another random variable, and it's the sum of the first n of these xi's. Okay, so it's the sum from I equals 1 up to n of the xi's. Okay, so I'm adding them all together. Now, obviously, depending on what the xi's end up being, Sn can take a plethora of different values, right? If n is 100, I'm adding up the first 100 of these things, then there's an awful lot of different potential values that I could get for Sn, because it depends what x1 is, and it depends what x2 is, and x3, all the way up to xn, whatever that might be. And the way that I'm going to define a random walk is I'm going to say that a random walk is the stochastic process Sn, where n is a natural number. Okay, so what this is basically the process or the sequence S1, S2, S3, S4, all the way up to infinity, and it goes on and on and on forever. Sometimes it's pretty common to also include S0 here. So S0, I'll include it. And sometimes S0 is a random variable as well. Like sometimes it's randomly assigned. It could be X, we could have X0 here, and it could be either 1 or -1. Sometimes, and normally, S0 is just going to be a number, and normally it's just going to be 0. So for a simple random walk, S0 is deterministically the number 0. So this is just the number 0. That's it. Okay, that's how we're going to define that. But other than that, this is a stochastic process. Now, it's called a simple random walk because you can kind of visualize this as a situation involving that. So let me, if you just indulge me for a second, I can kind of give you this analogy. So let's say that you are standing up, you're facing forward, and you toss a fair, let's say a fair coin for the time being. You toss a coin. And if it lands on heads, you take a step forward. And if it lands on tails, you take a step backwards. And you do this process again and again and again. You do it forever, okay? And that process, the places where you're going to stand, the distances that you stand from where you begun, that is your stochastic process. That is your random walk. And we can kind of draw this actually on a diagram as well and visualize this. So in the process of these videos, we are going to see a lot, many of these diagrams. So down here I've got n, and up here I've got Sn, and this is one potential situation. So again, I'm saying S0 is just going to be 0, so we're here. And let's say that x1, because remember Sn is just the sum of these xi's, let's say that x1 is the number 1, okay, with some probability p, it's the number 1. So this is an actualization of our random walk. So let's say that it's already happened, the random event, we can see what's happened into the future, and we're just going to record what happened, okay? Let's say the first value was 1, so we go up by 1. This is 1, this is 2, and then I've just done it up to 9 there. So the value of Sn is 1 for the first one, maybe. Then we toss a coin and maybe we take a step backwards again. So now we're going back to the origin on the second step. And then maybe we do our thing again, whatever it is, and we go back up. And then maybe we go up again, okay? And the probability that we go up is P, and the probability that we go back down again is 1 minus P, whatever that ends up being. And maybe we get something like this. Obviously, there's lots of ways that I could have drawn this, right? There's not just one way. There's loads of ways. And if I ask someone else to say, oh, just draw this random shape, they would probably draw it differently. Okay, and it could also go below the x-axis. So we could our first random situation, our first x1 might be the number -1, and so it's going to look like this. And then the next one, it might be -1 again, so we're down here. And then it goes 1, so we add 1 again. And then we go back, now we're at 0 again. And you can imagine that we're just going to get this this random situation like this. Okay, and of course I could just keep doing this. It's kind of fun. We can just keep going and going and going. And you guys get the idea that this is another version of what our random walk could have turned out to be. There's lots of ways to do it. But this is the idea of a random walk. And you can ask all sorts of questions about a random walk, all sorts of things. So what we're going to do in this video is we're going to see if we can work out the probability. I'm going to write this down. I'd like to know the probability that Sn is equal to 0. So for a specific value of n, what is the probability that it's equal to 0? So what I mean by this, just to make it really, really clear, is I give you a random value of n. I give you a value of n, whatever it might be. Let's say it's number 6 or something like that. What is the probability that when n is 6, we are at 0? We are back to where we've started. Okay. What is the probability of that happening? Obviously, it's going to be in terms of n, because if n is really, really, really big, then the probability is going to get smaller and smaller that we're, at 0 again. If n is small, the probability will be a bit bigger. But we're going to do that. That's one thing that we can do. We're going to do this right now. But you can imagine this is just one of many, many, many things that we can do. And before we actually do this example, let me just talk about the kind of real life situations, aside from walking forward and backwards, that a random walk can model. So a simple random walk could describe maybe some sort of gambling game where you enter a game and you either win money or you lose money. And of course, you can play this game over and over again. And this time, instead of n being the number of times that you toss a coin, maybe this is the number of times that you play the game. Maybe you play a game, it costs £1 to enter. You either win your money back plus £1, or you just lose and you don't get anything, right? This would be a simple random walk, okay? Because you either get your money back plus £1, so your total money goes up by 1, or you just lose your £1, and so your money goes down by 1. And maybe I want to know, for example, we're going to do this in a second, maybe I'd like to know, if I play the game n times, what is the probability that I've not made any money, but I've also not lost any money? I'm just where I've started. So that's one situation. Gambling is a very, very common paradigm to think about a random walk. Let's actually do this question though. So the question is, what is the probability that Sn takes the value 0? Okay. Now, just to be clear, let's actually write down what this represents in our sigma notation. So Sn, remember, is just the sum from I equals 1 to n of these xi's. And these xi's can take the value 0, or sorry, it can take the value -1 or 1. Okay. So we need this sum to be equal to 0. Now, let's just think about this for a second. Is it even possible for this to work if n is an odd number, right? So just going back up to the diagram for a second, it's not even possible for Sn to be 0 if n is odd, right? Because you start at 0 and then you go up, down, down, whatever you do. But you can see that the only way of getting back to 0 is on an even numbered game or toss or whatever you're talking about. So we have to split this into two cases. Okay, we're trying to find this probability. So we can see that if n is odd, the probability that Sn takes the value 0, hopefully it's quite clear that this is just 0. It's impossible for it to take the value 0. If n is even, there's a bit more to the story, and we're going to do that. So if n is even, I'm going to say that n is 2k, where k is a natural number. And what I'm then going to work out is the probability that the sum from I equals 1 to 2k, because that's just what n is, of xi is equal to 0. Now, again, let's just think about this for a second. So in order for this to be true, I basically need k plus 1s, and I also need k minus 1s, if that makes sense, to get back to 0. I need exactly k ups, and I need exactly k downs. I don't care whether they're all up, k times, and then down, 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 down. I don't care about whether it's like that, or it could be up, down, up, down, up, down, up, down. There's k ups, there's k downs. I don't care which order it is, but I do need a total of k ups, and I need k downs. That's what, in order to get back to 0. In some way, shape, or form, this has to happen. Now, guys, let's just think about this for a second. There's 2k trials, you could say, tosses of a coin, times that you're going to enter some sort of gambling game. The probability of success, getting an up, is fixed. It's p, right? So p is the probability of success, whatever that might be, 0.5, 0.6, whatever you want. Could be 0.1, could be that the tendency is to go down, doesn't matter. The probability of success is fixed. The number of trials is fixed. This looks like a binomial situation, okay? And it makes sense because we're adding stuff up. We're adding up things that kind of look like Bernoulli random variables. Binomial should be on our mind. So what I'm going to do is I'm going to replace this probability with something else. I'm going to say this is the probability, and I'm going to explain this in a second, that y is equal to k, okay? Now, I've not said what y is. Let's talk about that. I'm going to say that y is a random variable that is binomially distributed with 2k trials and a probability of success of p. Okay. Now let's just, we're doing a lot right now. Let's just make sure this makes sense. So we've got 2k trials. The probability of getting a success is p, and we want there to be exactly k successes in order to have k ups and then k downs. Does that make sense? I hope so. So all I want is the probability that y takes the value k. That means there are k successes. This is just a binomial question. Well, what is this? What is it? Well, we're just going to use the formula for binomial probabilities. Okay, and if we know that, and again, 2k is the number of trials here, so it's going to be 2k choose k times the probability of success to the power of k times 1 minus the probability of success to the power of 2k minus k. This is literally just, all I'm doing right now, guys, is I'm just using n choose x times p to the x times 1 minus p to the n minus x. Okay, this is just the probability mass function for a binomial random variable. That's all I'm doing. That's literally all I'm doing. And of course, we can simplify this ever so slightly. This is 2k choose k times p to the k, and then I'm going to opt to use q instead of 1 minus p, but some people like to just keep it as 1 minus p. I'm going to use q to the power of k. Remember, guys, just in brackets, q, remember, it's just 1 minus p. So this is the probability of a failure, you could say. Okay, that's all q is. That's by definition, that's what it is. I'm not doing anything mathematical, just renaming 1 minus p. Lovely. So this is the probability if you have 2k trials, or if you're 2k different tosses or steps into your stochastic process. This right here is the probability that you are going to be back to 0. Okay, not necessarily for the first time, you're just at 0. Maybe it's the second time, maybe it's the 100th time, depending on what k is. But this is the probability that you are at 0 after 2k trials or 2k steps in your stochastic process. So final answer, guys, final answer. The probability that Sn is equal to 0 is two things, okay? So it's a piecewise kind of situation. It's two things. So it is 0, impossible, if n is odd. So if n is odd, it's 0, okay? And if n is even, then I'm just going to use this. But remember, I said n is 2k. So I'm just going to go back a little bit. So if n is even, then it's basically n choose n over 2 times p to the power of n over 2 times q to the power of n over 2. And that is if n is even. So there's no issues with dividing n by 2. It's still going to be a whole number because n is even for sure. And this is the answer. So in a simple random walk with a probability of going up of p, the probability that on the nth step you are back at the origin, you are back where you started, is given by this here. Okay, so it's impossible if n is odd, and it's that thing there if n is even. That is a really, really well-known, very useful, common situation. But at the end of the day, ultimately, it's just binomial. So it's interesting, it's cool, it's one thing that we can do, but we're going to go a lot further than this. We're going to go beyond this in future videos. So for example, in the next video, what we're going to try and do is we're going to see if we can find the probability that S2A equals S2B equals 0. So what does that mean? Well, we're going to find the probability. So let's say that A is less than B, just without loss of generality. A is a number less than B. The probability that for some number 2A is just an even number, that number of steps, after 2A steps, we're at 0. And then after 2B steps, we are also at 0. Okay, so in the next video, this is just the same thing as the probability that after 2A steps, we're at 0. So we've already just done that. But also, then after 2B steps, again, we're saying B is bigger than A. So later on, we're back at 0 as well. Now you might say, wait a second, can't you just times the two probabilities together? Like have we not just worked this out? The trouble is that the probability that S2B is 0 is not independent of S2A being 0, because it's the same stochastic process. So these two things are not independent. So it's actually a bit harder than you might suspect that it is. But in the next video, we're going to look at this. So stay tuned for that. If you enjoyed the video, then first of all, I appreciate that. And, thank you so much for supporting the channel. And please do, as always, guys, leave comments. If there's anything I can do better, if there's anything you don't understand, I'm inviting you right now to go and check the comments out. And you can ask me any questions that you want, and we're going to get to the bottom of it. But thank you so much for watching, guys, and I'll see you in the next one. Cheers.